All right, welcome back to Simple Harmonic Motion, everybody. Today we're going to be talking about the springs, but going in the vertical direction. So maybe it seems a little intimidating, but it's actually not really that big of a deal. So even though it is vertical, we're pretty much going to be doing everything similar to how it always is. Anyway, let's look at these problems and everything. So if the spring is hung vertically, the equilibrium position changes. The equilibrium position is the point at which the spring force equals the gravitational force. The placement is now measured from the new equilibrium position. Okay, so without the mass, we can see that this is the equilibrium position because nothing's pulling on it, nothing's stretching on it, there's no force, and it's like that. But when there's a mass on it, the equilibrium position changes because the point at which the net force is zero becomes lower. Now there is going to be a force of the spring pulling it up, but there's also a force of gravity pulling it down. And the new equilibrium position will be when these two are exactly equal to each other and they cancel out. Okay? So that's why the equilibrium position changes and lowers. But other than that, that's pretty much the only thing that's different with these vertical mass spring system problems. But anyway, let's try some problems out. So we have a 2 kilogram block is attached to an unstretched spring of spring constant 200 Newton per meter, as shown in the diagram. It is released from rest. Determine the period of the block's oscillation. So just because it's a vertically positioned and not horizontally positioned, mathematically it's going to be the same exact thing. We have the period is equal to 2 pi square root of m over k. So we're just going to be plugging all this in. Period is equal to 2 pi square root of mass, which is 2, k, which is 200. Plug this into our calculator and we should get our answer. Square root of, 2 divided by 200. And we should get around 0.63 seconds. Okay, so again, even though it seems different, we can treat it the same exact way because mathematically it works that way. Okay, so let's look at example number 18. A 2 kilogram block is attached to an unstretched spring of spring constant 200 Newton per meter, as shown in diagram. If it is released from rest, what is the maximum displacement of the block from the equilibrium position while it's undergoing simple harmonic motion? Okay, so this is an interesting problem. So what we have is, it's not shown here, but we have a spring, and the spring is something like this. And then when the block goes onto it, it kind of sags down more this way. We can see it get attached to it, so then it elongates like this. So what we know is if we put a block on this, right? If we put a block on this and release it as the problem is asking, what's going to happen is it's going to start going up and down and up and down and up and down. It's going to oscillate from this new equilibrium position right here. Okay, so there's going to be a new equilibrium position, and it's going to oscillate up and down from that equilibrium position. So all we're going to be doing in this situation is trying to find what this new equilibrium position is in relation to the original equilibrium position. Okay, so all we're going to do is what we know the new equilibrium position is going to be here. And how we're going to find that is we know that the force of gravity is going to be equal to the force of spring. And how we know that is at the equilibrium position, remember that the force of gravity is equal to the force of the spring. So we know the mass is 2, gravity is 10, and then force of spring is kx, so the k is 200, and then x, this kind of shows how much it's going to stretch. Okay, so if we have this, we have 20 divided by 200. And what we get is 0.1. So what that means is if we have it here and then we release it, it's going to go 0.1 past the equilibrium, and then it's going to come back up 0.1 and just going to oscillate forever like that, 0.1 meters away from the new equilibrium position. Okay, moving on. So we have an object of mass 8 kilograms is attached to an ideal massless spring and allowed to hang. The spring stretches 3.6 centimeters before it reaches its equilibrium position. If this system is allowed to oscillate, what will be its frequency? Okay, So we're looking for frequency here. But when we see this, we should know immediately that frequency is equal to the 1 over the period. So if we can find the period, we should have no problem finding the frequency. And we know period is equal to 2 pi times mass. Whoops. They give us the mass. Oops. Mass being 8. Oh, but we don't know what K is. Okay, so what does it say? The spring stretches 3.6 centimeters before it reaches equilibrium position. Okay, so we're going to do what we did with the last problem. We know at the new equilibrium position, the force of gravity is equal to the force of the spring. So we have force of gravity as 8 times 10. And this will be equal to K times X. And X is 3.6 centimeters, which is 0.036 meters. So now we can find the spring constant. 80 divided by 0.036. And we get a spring constant of 2,222.22 Newton per meter. So we can put that over here, 22222. And now we can find what the period is. So let's see, square root 8 divided by 2222.22 times 2 pi. And then we're going to see the period is equal to 0.38 seconds. And now we can find the frequency. Frequency 1 over 0.38, which is going to give us frequency 1 divided by answer, 2.65 seconds. Okay? Not seconds, hertz. So it oscillates 2.675 times in 1 second. Okay? All right. Now let's look at this problem. We have a 12 Newton object is oscillating in simple harmonic motion at the end of an ideal vertical spring. Ideal vertical spring. Its vertical position y as a function of time is given by 4.5 centimeters cosine 19.5 radians per second t minus pi over 8. Minus pi over 8. What is the spring constant? Okay. So there's a few things we should know here. We should know that this is the amplitude, this is omega, and this is the phase constant. Okay, so we're going to use this omega here to help us out. So if we know omega is equal to 19.5, what that's going to tell us is we also know 19.5 is equal to 2 pi divided by t. What this tells us again is this tells us what t is going to be. So I can do 2 pi divided by 19.5. And then what I get is 0.32 seconds. Once I find the period, now what I can do is I can find the k value, because I know that t is equal to 2 pi square root of m over k. So I have 0.32 is equal to 2 pi square root of m. Mass is going to be 12 divided by 10, so 1.2 divided by k. Now this is just an algebra problem. So divided by 2 pi squared. 1.2. And we get that the k is around 456.3 Newton per meter. Okay? Okay. Now let's look at this. What is the maximum acceleration of the object? Okay, so we have the position as a function of time, but let's now do the derivative of this to find what the velocity is and then what the acceleration is. So this right here, I don't actually have to write all this out. Maybe I should. Maybe, okay, so let's first do this. It says, what is the maximum speed that the object reaches? So I'm going to do C first. Okay, so I know that the position as a function of time is equal to 4.5 centimeters times cosine 19.5 t minus pi over 8. Now I know that the velocity as a function of time is going to be equal to 4.5 centimeters times 19.5 if I do the chain rule, 19.5. And then this is going to be minus, it shouldn't be minus, it should be negative. So this is, I'm changing this cosine to sine, so sine 19.5 t minus pi over 8. But then this is all negative. And what this is going to give me, this is going to give me the maximum velocity, 4.5 times 19.5. So if I do that, 4.5 times 19.5, I get the maximum Vmax as 87.75 centimeters per second, because this is measured in centimeters. Okay? Because the reason why that's the maximum velocity is because this value over here, this sine and t and everything like that, the largest number this could ever be is 1. So that means the largest value that the velocity could ever be is 87.75. Okay? It can't ever be more than that, so that's why this is the largest value here. Okay, so let's move on. Now we have, Now we have, 17 point. Okay, sorry about that. Okay, now let's look at the acceleration for the acceleration. Now we're going to find the derivative of this acceleration as a function of time is going to be equal to negative 4.5 centimeters, 19.5. And now we're doing the chain rule again. We're bringing this down. So this is going to be 19.5. Now we're going to have cosine of 19.5 times t minus pi over 8. So now we're just doing this, and we see that the acceleration max is going to be 4.5 times 19.5 times 19.5. And then we get 1711.13 centimeters per second squared. Okay, if we wanted to convert that to meters, we could, but that's how it is without converting it. Okay. Now it says, how long does it take the object to go from its highest point to its lowest point? So if it's oscillating from its highest point to its lowest point, that is half a period. And half a period is going to be 0.32 divided by 2. So that's going to be equal to 0.16 seconds. Okay. All right, guys. I hope that all made sense. Next time, what we're going to be going over is multiple choice questions. All right, thanks for watching, guys, and I'll see you in the next one.